Hello everyone, I hope you all are having a great day. And today, in this video, I would like to explain about our differential equation assignment 1, code Ssce 1793, overlooked by Dr. Nur SYARAFINA. And as the representative of Group 8 giving this introduction, I would like to explain about what we have in this video and what you guys can look forward in our video. Firstly, let me introduce my fellow group members. Firstly, we have VOON JINGRONG, Nur FARAH ELENNA, Jing, Hui, Nur ADREENA ALIA, and lastly, myself ARESSH, doing this introduction. In this video, we will explain about mechanical vibrations and the different type of mechanical vibrations alongside an example to give you all a better understanding about mechanical vibrations and its application based on our chapter 2. Now I will explain more about mechanical vibration and to give you all a better understanding and give the gist of this topic. Firstly, mechanical vibration. What is mechanical vibration? Well, the general meaning or the base definition of mechanical vibration is measurement of a periodic process of oscillation with regard to an equilibrium. I think all of us understand what is an oscillation. Oscillation is a swinging motion or traveling motion from one point to another with regard to an equilibrium point. That means equilibrium point is the starting point that we have to go and return back to its original state. That is known as equilibrium point. And the equation that we use to calculate mechanical vibration in our topic today is my double prime plus by prime plus ky equals to f in the brackets t. Okay, what is m? M is the mass. I think that's fairly simple and all of us know what is mass. What is b? B is damping coefficient. What is k? K is spring constant. And finally ft, or the value that we are looking for, which is force, or we can also call it as external vibration. I will explain more about what is damping coefficient, or in the equation we can see as b. Damping coefficient is a material property that indicates whether a material will bounce back or return energy to a system. For instance, a spring with a load. When we attach a load, the damping coefficient, the spring will generally go down, and once we release the load, the spring will go back to its original state. That is known as damping coefficient, or the ability for an object, or in simpler terms, for a spring to return to its original size. And what is spring constant? And spring constant is a characteristic of spring which measures the ratio of the force affecting the spring to the displacement caused by it. Okay, I gave you all the general meaning of spring constant, but in simpler terms, spring constant is basically the stiffness of spring. Okay, for example, I think most of us have used this when as a child, a slinky spring. It has multicolored one and we can release it and it will travel and it will move. A slinky spring has very low spring constant. That means it's very not stiff. That means it's easily breakable and it's easily stretchable. Whereas a spring that we use in experiment or in our laboratory has high spring constant, which means it's much more stiffer and it takes a lot more for it to break or for it to disembed the shape.
Hi, my name is Hui, and now I'll explain about the type of vibrations. So, first and foremost, we have 4 types of the vibrations. We have the undamped free vibrations, we have damped free vibrations, and then we also have the undamped force vibrations and also the damped force vibrations. So now I will cover for the type 1 vibration, which is the undamped free vibrations. I will start to explain the meaning of undamped free vibration. So undamped means that no energy is lost with the movement. So an undamped system will vibrate forever without any additional applied force. So now let's move on to the free vibrations. Free vibrations is the vibrations when the external force is removed after giving the initial displacement to the systems. And then for the undamped free vibrations, it will happen when there is no external resistance or dampings to the vibrations. So from the general equations, ny second derivative plus ky is equals to f in the variable of t. After that, we'll rearrange and we'll get the equations for the undamped free vibrations is become my second derivative plus ky is equals to 0, where here the m will be represented for the mass and k will be represented for the spring constants. So for these undamped free vibrations is a type of the homogeneous equations. And now I will pass the presentations to ADREENA.
Hi, I'm ADREENA and I'm going to explain a little bit on the second type of vibration, which is the damp-free vibration. So damp-free vibration basically means that there are no vibrations involved but with the presence of a damper. The general equation is my second derivative plus by first derivative plus ky equals to 0. The 0 here indicates that there are no vibrations involved, so this is a homogeneous equation. So how exactly do we get this equation? It is actually from the general equation of the mechanical vibration, which we know as my second derivative plus by first derivative plus ky equals to ft, where m is the mass, b is the damping coefficient, k is the spring constant, and ft is the force of vibration. So next, I'm going to talk about the easiest damping method, which we will use as an explanation for this type, which is the viscous damping. Viscous damping occurs when a piston in a certain fluid has some viscosity. The piston will move in the fluid, causing the fluid to flow through the orifice of the piston, which will make the differential equation to be linear with F equals to CV, where F is the damping force, C is the damping constant, and V is the relative velocity. So in this picture, we can see that the force exerted by the damper is proportional to the speed, which is y, at which the piston moves and is directed in the opposite direction from the movement of the mass. By doing the free body diagram here, assuming that both displacement and velocity is in the positive y direction, and we will get this equation with negative ky minus by first derivative equals to my second derivative. And by arranging it, we will get the damp-free vibration equation, where my second derivative plus by first derivative plus ky equals to 0.
Hi, my name is JINGRONG and I will be present about the type 3 of the mechanical vibration, which is the undamped force vibrations. So, what is meant by undamped force vibrations? The undamped force vibration means that there is no damping in these mechanical vibrations. And the general equations of the undamped force vibration will be the m second derivative of y plus ky equals to ft. But how does this general equation of type 3 undamped force vibration comes from? Remember the general equation of the mechanical vibration? Yes, this general equations of type 3 is come from the general equation of mechanical vibrations. So you can see that the general equation of the vibration is m second derivative of y plus b first derivative of y plus ky equal to ft. Since that there is no damping in this type 3 vibration, therefore we can cancel it. So now the equation we have is the general equation for type 3 undamped vibration. And you can see that since that the general equation is equal to ft because of the force vibrations, therefore this equation is a non-homogeneous equation because it is not equal to 0. It's equal to ft, which means the force vibration. That's all for the type 3 undamped force vibration. Thank you. And I will pass the presentation to FARAH.
Hi, now I'll be presenting on the fourth type of mechanical vibration, which is the damped force vibration. So first of all, we need to know what is damping. So what is damping? Damping is a mechanism of absorbing the vibration of energy. And the damping element symbol is as shown in the diagram on the upper right. On the the big title. When talking about damping, there is 3 types of damping, which are viscous damping, column damping, and hysteretic damping. For viscous damping, as an example, the dashboard or the shock absorbers of a car consists of a cylinder piston where the fluid or the oil inside the cylinder resists the motions of piston, thus absorbing the motion of energy. The second type of damping is column damping. As an example, when we have an object move on a rough surface, we will get a friction force against the motion of the object, which it absorbs some of the kinetic energy. And lastly, for hysteretic damping, it exists in a warm structure where it is subjected to vibrations. The vibration energy in the structure is dissipated by the friction between the internal planes and the materials. Next, before we go deeper on the equation explanation, I'm going to explain about the damp force vibration in general. So, generally, all elements are involved in damp force vibrations, which are the spring and damping elements. The general equation of damp force vibration is as shown in the slide, which is my second derivative plus cy first derivative plus ky equal to f in t variable. This equation is summarized from the diagram in the slide shown. From the equation, we know that damp force vibration is a non-homogeneous equation because the equation is not equal to 0. Now, I will be explaining on how do we get the general equation by the equation of motion. So, first of all, as you can see in the diagram at the left side, we could see that the K and C is in the negative sign as it goes downward, while the X, M, and F is a positive sign as it goes upward. So how do we get positive and negative sign? It is by following the sign convention of physics, where when we go upward or to the right, we will get a positive sign, while in contrast, for going downward or to the left, we will get negative sign. Now, by following the Newton's second law, sigma f equal to mx second derivative in t variable, we could arrange the algebras from the diagram into the equation, which is f minus kx minus cx first derivative equal to mx second derivative in t variable. After doing so, we rearrange the equation into mathematics equation, which is mx second derivative plus cx first derivative plus kx equal to f in the variable of t. For your information, the m in the equation is referred to mass, while the c in the equation is referred to damping coefficient. The k is referred to spring constant, and the f in the equation is referred to the force or external vibrations. So that is how we get the general equation of damp force vibrations. So that is all from me. I'll pass to the next presenter.
My name is Jing, and I'm going to continue with the example. The question is, a mass m is projected vertically upward from origin with initial velocity v0. Find the maximum height reached, assuming that the resistance of the air is proportional to the velocity of mass. The solution is, we take upward direction from origin as positive. The mass is acted upon by two forces, which is the gravitational force of magnitude mg and the resistance of magnitude kv, both directed downwards. The motion of the mass and the forces acted upon are illustrated in the figure below. Thus, at time t, let x denote as the height of the mass from origin, h is the maximum height from origin, v0 is the initial velocity, v equals to dx dt is the velocity of the mass, and d square x dt square is the acceleration, mg is the magnitude of the gravitational force downward, and kv is the magnitude of the air resistance where k is a constant. So the figure shows the motion of the mass and the force act. From Newton's second law, we get mass times acceleration equals to resultant force. After arranging the equation, we get d square x over dt square plus k dx dt equals to negative g, where k equals to mk. The first step will be determine the YH. YH will be AE power negative KT plus B because it is two distinct roots. And the second step is to determine FT and YPT. So the FT will be negative G, and the YPT equation is T power R times C0. R equals to 0 is rejected because YP equation has a similar term with YH, so we will consider R equals to 1, which YPT equals to T times C0. After calculation, we get C0 equals to negative G over K, and the YPT will be negative G over K. After adding YH and YP together, we get X equals to AE power negative KT plus B minus G over K times T. Next, we will consider AE power negative KT plus B minus G over K times T as our second equation. So after differentiating the equation, we get negative K times AE power negative KT minus G over K, and this will be our third equation. To find the maximum height, we need to find the values of A and B. For this purpose, we consider the associated conditions as in A, B, and C below. So from equation 2, when t equals to 0 and x equals to 0, we get A plus B equals to 0. And from equation 3, when t equals to 0 and v equals to v0, we get A equals to negative v0 over k minus g over k squared. From the fourth equation and the fifth equation, we get b equals to v0 over k plus g over k squared. Substituting the fifth equation into the third equation, when v equals to 0, we get t equals to 1 over k ln g plus k v0 over g, and this equation is the time taken to reach the maximum height. So after substituting the 5th, 6th, and 7th equation into the second equation, we get our final answer, which is x equals to 1 over k times v0 negative g over k ln g plus k v0 over g. And this is our final answer. That is all from us for today. Thank you.